Okay, let's consider example 2. In this case, we have a word problem. So we have a company has determined that its production level is given by the Cobb-Douglas function of um, f of xy equals 2.5 x to 0.45 times y to the 0.55, where x represents the total number of labor hours in 1 year and y represents the total capital input for the company. Switch to green. So x represents total number of labor hours. Suppose 1 unit of labor costs $40. So $40 goes with X. Whereas Y represents total capital input, and that is 1 unit of capital input costs $50. Okay, so in this situation, so use the method of Lagrange multipliers to find the maximum production level subject to a boundary constraint. Constraint's a keyword of $500,000 per year. So I have my function that I want to maximize. I want to maximize f. And my constraint function is g, but I'm not given the constraint function g. I have to come up with it based on this situation. So the constraint is that the budget, I'm limited by the budget of $500,000. What is the budget made of? It's made of um, how much labor costs and how much capital costs. And how much does labor cost? It costs 40 times labor hours. And how much does capital cost? It costs 50 times capital input units, whatever those are. And so those add together is limited by 500,000. So that means if I were to say move the 500,000 over to get 40x plus 50y minus 500,000 equals 0, and I can write my constraint as an equals 0 equation, then what I have right here, that's g of xy. Okay, and so then the whole equation is one of my equations. Now the other equation I have is that the gradient of f is equal to 2.5 times 0.45 times x to the 1 minus 0.45 would be negative 0.55 times y to the 0.55 I plus 2.5. Now I take the derivative with respect to y. And so with respect to y, I'm multiplying by the power rule. So 0.55 times x stays the same because I'm treating it like a constant. And then y becomes 1 minus 0.55, which is negative 0.45 j. And the gradient of g is equal to 40i plus 50j. Okay, so that gives me 3 equations. So turning this from a kind of a calculus problem into an algebra problem, I now have, well, let me first pause and do the calculation of 2.5 times 0.45 on my calculator. Okay, so on my calculator, it says that 2.5 times 0.45 is 1.125. So 1.125, and let's write, instead of having them written like that, let's write them as y to the 0.55 over x to the 0.55 equals lambda times g, x component, which is 40. And then also if I do 2.5 times 0.55, I get 1.375. So 1.375 times x to 0.45 over y to the 0.45 equals lambda times 50 for the j component. And then I have as well, 40x plus 50y, 40x plus 50y. And then you could have like, I could use this form, like minus 500,000 equals 0, but I'm going to use the original form, equals 500,000. Okay, so here I have a situation that's not linear, which means I don't get to make a nice little calculator thing and do a matrix calculation here. But in some ways it's simpler because as long as, let's see here. So this is a situation when we get to try, I get to show you another kind of technique for solving these problems. And one of the good techniques for solving these problems is that we don't care what lambda is. It just has to be the same in both equations, or in all three equations if you're doing 3 dimensions. So that means if we solve for lambda, we can set these things equal to each other and then solve for x and y. And once we have like get down to 2 variables, it just is more manageable. So I'm going to say divide 1.125 divided by 40. So I'm going to calculate 1.125 divided by 40 is so 0.028125 y to the 0.55 over x to the 0.55 equals lambda. And also taking 1.375 divided by 50 is 0.0275. So 0.0275 x to the 0.45 over y to the 0.45 also equals lambda. That means these things are equal to each other. So setting them equal to each other means that 0.028125 y to the 0.55 over x to the 0.55 equals 0.0275 x to the 0.45 over y to the 0.45. Okay. Well, I can get rid of fractions by multiplying both sides by y to the 0.45 and x to the 0.55. And I get 0.028125y equals 0.0275x. And so now I happen to have kind of accidentally stumbled upon a linear equation. So now I have 2 linear equations with 2 variables. I feel I could just solve for y for both of them. Or I could do this with a matrix calculator. Let's just solve for y this time. So y is going to be so 0.0275 in my calculator divided by 0.028125 in my calculator gives me 0.9 and then 7 repeating. So y equals 0.97 repeating x. So that means that I could over here substitute. And so 40x plus 50 times 0.97 repeating x equals 500,000. Which means that I've got 40 x's plus 50 times 0.9 and then 7 repeating of those x's, which is 88.8 repeating. That means I've got 88.8 repeating x's equals 500,000. So X equals 500,000. 1, 2, 3 divided by 88.8 repeating. And I get 5,625. So X equals 5,625. And then Y is that times 0.97 repeating. So times that times 0.9 and then 7 repeating. And I get 5,500. So Y equals 5,500. Okay, which makes that is the only critical point. So it's going to be the maximum. But I can always double check that if I'm unsure. So I could easily have taken the endpoints of this, because if I plug in endpoints of like all X's and no Y's, then I'll get 0 profit. If I have all capital and no people, I get 0 profit. All people and nothing for them to work on, no capital, then I have 0 profit. So that makes this most likely maximum. All right, that finishes that example.